Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we discuss a concept of boundary layer thickness and displacement thickness. So this is another part in the boundary layer theory. So in the last lecture, we have seen what are the different types of layers are there and what are the different types of zones are there, like laminar zone and turbulent zone and laminar sublayers, transition zone. These are the zones we have seen in the last lecture. So boundary layer thickness actually uh, this boundary layer thickness actually it is defined as, like, it is denoted by delta. It is denoted by delta. And how it is defined, let me suppose consider a solid body is there, and when the fluid is flowing, we know that when the fluid is flowing over the solid body, suppose this is the solid body is there, and it is suppose not moving, it is in fixed condition. So obviously there will be a boundary layer formation will be there in this way, like what we have seen in the previous. So now this boundary layer thickness actually is nothing but the thickness from this boundary, like the thickness from the solid body, you can say, from this solid body to the layer where the velocity, the local velocity will be equal to the free stream velocity. Suppose I'll take this distance, then this distance is called your delta, boundary layer thickness. If I consider this distance, then this distance also called as a boundary layer thickness. That means here inside this, all these velocities are local velocity. Already I told you in the previous lecture. Now when this local velocity is going to be free stream velocity, now at this point, at this layer actually, at this layer, the velocity, this fluid velocity will be 99% equal to the free stream velocity, u or u infinite. So this distance, like from this surface to this layer, that is called delta. So we can say it is defined as the distance from the boundary, of the solid body. That means suppose this is the boundary of the solid body, and in it one more thing, we need to consider only y direction. We need to consider in the y direction, and the distance from this solid body to this boundary, where we can say this local velocity is approximately 99% equal to the free stream velocity, and that is denoted by the delta. So in the last lecture, we have seen that this is laminar zone, this is laminar zone, and this is laminar boundary layer, and this is next to that some transition zone is there. Then after that, turbulent zone is there and turbulent boundary layer. So all this boundary layer what we have seen, so this delta also will be different for that. So what we can write now for laminar, we can write this is delta laminar. So delta and laminar equal to what? This is the thickness. This is the thickness of laminar boundary layer. Similarly, delta for turbulent. Delta turbulent equal to same thing, thickness of this is turbulent boundary layer, TBL. And similarly, one more is there, that is a sub layer, that is laminar sub layer. So this one we can write thickness of laminar sub layer. Okay, this is delta dash. So these are the indications are there for the boundary layer thickness. Now we will discuss about the displacement thickness. So displacement thickness actually, this displacement thickness is also a very good concept in this fluid mechanics. So this displacement thickness actually, it is defined as delta star. This is delta star. Okay, now this one we have taken delta, and this is now delta star. So this displacement thickness, how to define? Actually, for this also one definition is there. So this is also defined, we can say the distance. This is, we can write the distance, let me write distance measured perpendicular. So everything we need to consider in the perpendicularly in the y direction. Distance measured perpendicular to the boundary of the body, to the boundary of solid body. Okay, and by which we can say, by that the boundary should be displaced. The boundary should be displaced. The boundary should be displaced to compensate for the reduction in flow rate, to compensate in reduction in flow rate on account of, on behalf of, we can say, on behalf of boundary layer formation, on behalf of boundary layer formation. Okay, and this is the definition of this boundary layer, displacement thickness. So the distance measured, it is defined as the distance measured perpendicular to the boundary of the solid body. By that, the boundary should be displaced to compensate for the reduction in flow rate. So keep in mind this flow rate term, just to remember, because remaining two thickness we are going to discuss after this, like momentum thickness and energy thickness, the whole definition will be same, only the flow rate part will be changed. Like this word will be changed for the remaining two things. When we will discuss about the momentum thickness, the reduction in momentum. When we are going to discuss about the energy thickness, only it will be changed, this term will be changed, like energy thickness. Okay, remaining all the terms will be equal, there is no change in that. So what is the meaning of this? Suppose this is the diagram what we have taken in this, I'll do. So there is a fluid flow is there in this solid body. What is the solid body? This is the solid object what is present here. Okay, now this solid body is fixed here and there is a fluid flow is there over the solid object. Okay, now according to this definition, okay, if there is no plate is there, if there is no plate is there, suppose there is no plate is situated, so how the fluid will be flows? In this way. So all this fluid will be flows in the free stream velocity, that is capital U. Correct. Now, so everywhere your flow rate will be same. Now, when you put some obstruction or when you put some plate in that, obviously there is a boundary layer formation will be there, and due to this boundary layer formation, we will get some kind of velocity gradient or velocity distribution in this way. So if you will get like this, okay. Now two things are there at this point, at A point and B point. So both points are differs, because here the fluid is going to strike here, and up to here your velocity is capital U or U infinite, anything you can consider, U or U infinite, anything we can consider. So now the next thing is, in this point at the B point, you can see the B point, yeah, at the B point the velocity is what? The velocity is local velocity, that is small u. So there is a difference is there. How the small u came formation happened? Due to this plate. So once the plate is there, then we won't get this free stream velocity. We'll get the velocity how? Near to the boundary, near to the surface of this one, it will be 0. Then it will be a slight increment, then again slight increment, then again slight increment in the velocity. So slowly, this velocity will be equal to the free stream velocity at this point. So there is a formation of velocity distribution is there, or velocity changes is there. Now at this point, we can say our small u is equal to u infinite or u. So you can see there is a, now at this condition, what happened? Your boundary, your flow rate will be different, and for this your flow rate will be obviously different. So here how much flow rate will get? Here will get obviously the more flow rate, and here will get less flow rate. So there is a gap, or you can see there is a loss of flow rate in this due to this plate presence. So to overcome these losses, or to to overcome this reduction, see, boundary layer should be displaced. So this boundary layer what we got here, that should be displaced to compensate for the reduction in flow rate. Now what is the flow rate was there? To compensate this flow rate, we need to what? We need to increase this, or we need to just compensate this one. We need to form a new boundary layer formations. Okay, after fulfilling this flow rate what was lost. So for that, what we'll do, we'll just increase some boundary layer formation at this level. Okay, now initially this is the losses of flow rate was there, because this is the gap what we got here, because velocity was changed here. Okay, velocity is reduced, and there is a velocity gradient formation happened. Okay, so to compensate this flow rate, so we need to displace this boundary layer. So that only boundary layer, the boundary should be displaced to compensate for the reduction of flow rate on behalf of boundary layer formation. So initially boundary layer formation was up to here. You can see initially the boundary layer formation was up to here. Now after that, the boundary layer formation will be like this. Okay, so this is the compensation happened. So, and this is actually, this is the change in this one is called your delta star, or that is called displacement thickness. So boundary layer displaced, that is the meaning. So let's see, let do one derivation for this delta star. So for derivation, already I have taken this diagram. So in this diagram only, I can, like, we can solve this theory. So what is the concept we need to consider? Like, AB point is given with a distance of x. So you can see, this is the distance. This is the distance from x point. So let's consider the fluid is flowing and having a free stream velocity which is equal to u, that already I told you. So let me write here. Suppose u is the what? U is the free stream velocity. U is the free stream velocity, and this fluid which is flowing over this one, that is u. Okay, and over a thin plate. So this is the plate what we have considered. Okay, and a distance of x. X is the distance from edge. Which one? From a point. Edge, you can write a, and distance from edge to section 11 section we have considered this one. A section 11 is considered at a distance of x. Okay, now the velocity of the fluid, we can see velocity of the fluid at this point. What? At this point we know that no slip condition is there. So velocity at the B point, velocity at B point equal to 0, and velocity at C, what will get there? You'll get the value of u. So this distance we know that, what is that? Delta, that is boundary layer thickness. So we can write BC equal to, what is the height from B to C point? That is delta. We can write this. Okay, and now let's consider a small elemental strip in this. Like, what is the how the velocity distribution formed here? See, this is the, suppose, B point and this is C point, and there is a velocity distribution in this way. Okay, now this is the velocity distribution. We know that velocity is changed layer to layer. Okay, and this is du by dy. Okay, now in this position, let me consider a small strip, small elemental strip in this one, that what we have taken here, a small elemental strip. Let's consider in this, in between this. So the small elemental strip with a height of, with a thickness of, you can see, this is y. Okay, that small elemental strip also we can write in this way, we can draw in this way. Suppose if you are seeing from this side, you can draw like this. This is actually y what is given. Okay, now this is dy actually, this is dy, and the distance which is present from this place, from this solid body, that is y actually. Okay, yeah, so this is y at a distance, and the thickness is the dy. Now if I draw this plate, okay, in 3D wise, so we can see this is the plate is there. Okay, this is the plate which is a thickness of y, and this width we can consider this is b. Okay, now so what we need to consider, a few things are there, like y is the distance, of the elemental strip from the distance of elemental strip from the plate, we can say, from the plate. Okay, similarly dy is the thickness, of elemental strip. Okay, similarly u, let small u equal to what? Velocity of the fluid, which is flowing in the elemental strip, that we know, that is local velocity. Okay, that I have taken already. And b already shown you, that is width of the plate. Okay, now actually the mass flow rate at this point should be equal to the mass flow rate at this point. So the flow rate what we are considering, that we need to prove it. and we need to equalize that one also. So what is the area of the elemental strip can be considered? So area of the elemental strip can be calculated. We know that this is B into dy, B into dy. This is the area. Now what about this mass flow rate or mass of fluid which is flowing over the elemental strip? Because we need to finally find out the flow rate. Okay, so the mass of fluid which is flowing over that elemental strip. Okay, the mass of fluid which is flowing over the elemental strip. So that one we can write. What is the formula of this? We know that rho into area into velocity. Okay, so rho into area into velocity. Area already we got here, so rho you can write this is rho, and velocity is we know that local velocity, that is small u, already I told you previously, and area we know that this is B into dy. Okay, so rho into B into dy. This is the mass of the fluid which is flowing over the plate. Okay, this is, let me give one equation 1. This is one condition when the plate is present. When the plate is present at this place. Now suppose I'll consider another one point. Suppose there is no plate is present. One more condition. Let's consider there is no plate is present. So no plate is present means I can write, let me show you here. Here there is no plate is present. Then what about this velocity, fluid flow? So when there is no plate is present, the fluid which is flowing with a constant velocity should be flows. So no plate means we can write the velocity should be considered u, or we can consider u infinite, whatever we can choose in that. So what about the mass flow rate? So the mass flow rate, or what is the mass of fluid? Same thing, mass of fluid, we can write mass of fluid per second which is flowing through the elemental strip, that to divide can be written when there is no plate. What about the mass fluid? That means the plate is present, that small strip, elemental strip is taken, and there is no plate, just what is the velocity is flowing, that is u. So mass of fluid you can write here again same thing, rho u b dy. Okay, this is equation 2. Now here we can see that u, obviously we know that u will be, that velocity of u will be more than the small u, because this is free stream velocity, this is local velocity, correct? Now, so the presence of plate we can due to the formation of boundary layer. So what is the reduction in mass flow rate? So next we need to, our target is to find out what is the reduction in mass flowing per second through the elemental strip, Okay, due to the presence of this plate, what is the losses happened? Elemental strip. First we need to find out the reduction in mass flow rate. So reduction in mass flow rate is nothing but we can write this is mass flow rate, that means mass per second, mass by flow rate second, what we got with respect to without no plate. Without plate we can write, and minus the mass of fluid or mass flow rate per second, with plate presence. That means equation 2 minus equation 1. So what I can write here, equation 1 is nothing, equation 2 is nothing but rho u b dy minus rho u b dy. So what will get here? Let me take common of rho b, and the bracket will be start capital U minus small u into dy, and this one you can give in equation 3. Okay, and the next task is, this is for only one elemental strip, correct? Now elemental strip is present what in this boundary layer is there, like means from 0 to, if you see, yeah, from B point to C point, elemental strip is present here. Okay, so now the total reduction in mass flow rate, we need to consider the whole area where we have taken this change in velocity gradient is there. So that next we can write the total reduction. This is only one small plate reduction we have taken. Now total reduction in mass of fluid per second. The total reduction in mass of fluid per second through the distance, through we can see BC, through BC due to plate, So just we need to integrate this equation. So what I'll write, integration of 0 to delta rho B capital U minus small u into dy. So you can take common outside, rho B take common outside, 0 to delta. Total height is delta, so I have taken delta. And this is capital U minus small u dy. Okay. And here, let's give this equation 4. Okay. If the fluid is incompressible, then it is constant, the density is constant. So that's why I've taken this one. Now, see, this is everything is happened. Now we need to display something to compensate that distance or that mass flow rate what we got. So now let displace the plate. So the next target is we need to find out, right? Here I can write, let the plate is displaced. The plate is displaced. The plate is displaced by a distance of del star, and the velocity of flow rate for a distance delta star, that will be equal to the free stream velocity. So the loss of mass flow rate, so the loss of mass of fluid, per second through the distance delta star. So okay, so what is this place it displaces talking? Let me show you. Here I have shown you that displacement thickness here, exactly the plate which is situated here. Okay, if just will be replace this one to the little bit height here. Okay, now see, now the plate is displaced from here to here. So how much displacement happened? That is delta star. So similarly, your boundary layer initially how much was there, now that also going to be displaced a little bit high, what I have shown you exactly here. Okay, due to this plate displacement here, how much displacement happened? A delta star. That is called displacement thickness. So that boundary layer also will be displaced here. So we need to find out this loss of mass of fluid through the distance of delta star. So that one also you can write here. What is that? Same thing again, rho into V. That means this is equal to U, and delta star is the displacement thickness, and what is the width is B. Same will be there as usual. Now we need to equalize this equation. Okay, this give this equation 5. Okay, now what we will do? You just equate this equation by equating equation 4 and 5. Equating equation 4 and 5, we can get what we'll get here. Just write this equation, rho B integration 0 to delta, and here capital U minus small u dy, and this is equal to what I can write, rho U delta star into B, because I need to find out what is the displacement thickness here. So displacement thickness I got it now. Now in this both side I can cancel this rho B and rho B. So what I'll get here, after cancelling this, we can write here the next sentence, integration 0 to delta capital U minus small u dy, and this is equal to capital U delta star. So what I'll do here, I'll just take delta star one side, because I need to find out the delta star equation. So what will get, 1 by capital U integration 0 to delta, okay, and this is U capital U minus small u dy. Okay, now again what I can write, this is, let me take inside 0 to delta U minus small u by capital U into dy. Okay, now again this one we can write, just to resolve this, what we'll get, we'll get delta star equal to 0 to delta. Now u by u, that will be 1 minus small u by capital U, small u by capital U, bracket close, and dy. So this is the final equation. Here you can give equation number 6, and this is the equation for the displacement thickness. Okay, so I hope you understand this concept of long theory. This is slightly lengthy, but it is not that much difficult to understand. Just we need to understand what is the this terminology, what I told you actually, that if you remember this formula, this definition, this is important. Actually, this definition is already given in the book, if you see. So in this, only we need to change for different thickness, only you need to change the term of flow rate. You can see the distance measured perpendicular to the boundary of the solid body. By that, boundary should be displaced to compensate for the reduction in flow rate. So what is the see what is the flow rate was there initially here? Suppose if I take this in this area, in this position flow rate, so both will be differs. So to compensate this change in flow rate on behalf of boundary layer formations. So to compensate this flow rate, we have changed the boundary layer formation, or we have displaced the plate. So how much change it happened? That is called displacement thickness. So similarly, this is flow rate was taken for the displacement condition. Similarly, if I discuss about the energy thickness, then on behalf of flow rate, I need to consider the energy, the kinetic energy there. Okay. Similarly, momentum thickness is there. Then there I need to consider the momentum. Only I need to change the word of momentum and energy in this. Remaining all terms will be same. Okay. So I hope you understand this theory part. Still, if you are having doubt regarding this, you can give a comment on the comment box. Thank you.